Hi, my name is Fatima, and today I'm going to talk about learning from uninterpreted sensory experience. I'd like to give a special thanks to my collaborators. So first, John Martin. We built off previous work he did with Joseph Modail, and our work was supervised by my thesis advisor, Michael Bowling. So we are focusing on the reinforcement learning problem, where we have an agent that sequentially experiences an environment online. At each time step, the agent receives an observation and a reward from the environment. And typically in RL, the agent responds by taking a subsequent action. However, we focus on the prediction problem, which limits the agent to a passive learner and does not include actions nor policies. So in the prediction problem, the agent tries to answer how much reward will I accrue up to some future time step. So I'm going to formalize this problem. So letting O be the set of all observations, the value function is a mapping from observations to the real numbers and is defined as the expected sum of future discounted rewards, where the Greek letter gamma is a number between 0 and 1, and it's the discount factor. And the prediction task is to approximate this value function. So within the context of prediction, we focus on computational perception. We simulate a frog's visual field as a 2D space of 4,000 sensors, shown in yellow and purple. And we place a target at the center, shown as the red circle. We also simulate the random movement of a fly moving throughout this space, and it's shown as the squiggly lines in mauve. So when the fly comes in close proximity to a sensor, the sensor will turn 1, otherwise it'll just remain at 0. And when the fly reaches the target in the center, the frog will receive a reward of +1, otherwise the rewards are just 0. So to generate a current observation, we corrupt this binary vector with noise by sampling a small percentage of the sensors and flipping their values from 0 to 1 or from 1 to 0. So the value function we want to learn quantifies the expected number of insects encountered in 100 steps. So the learner's main goal is to approximate the expected return with high accuracy given the observations and rewards. But recall that the raw observations are corrupted with noise, meaning that they are uninformative, and this makes the prediction task much more difficult. So there are some naive approaches we can use to approximate the return. The simplest one is just to use a linear architecture which ignores all patterns among inputs. Another approach is to use a biased architecture that imposes some prior information to relate inputs together and exclude other inputs. However, this, as I mentioned, this relies on prior information and therefore relies on an inductive bias. A third approach is to use a dense architecture which relates all inputs together. And if some inputs don't actually rely on others, then the architecture should learn to decrease those weights to 0 over time. The downside of this approach is that it's more susceptible to noise and also is more computationally expensive. So in order to be able to learn which inputs actually are useful, relate to one another, we use what is known as general value functions. These are auxiliary predictions or forecasts of arbitrary signals. For example, let's think about an agent that is learning to play the game of Wordle, and the agent wants to be able to predict the future return of the game. So to do this, it can also, it might be helpful to predict other signals. For example, the agent might also wonder how many green pixels I will see next, or how many time steps until I see a red pixel, or what color will be in the ith cell next. General value functions are formalized as the expected sum of discounted auxiliary rewards. These can be sound, color, internal predictions, or other internal signals. And we define these as linear functions of the observation vectors. So in order to approximate the value function, we incorporate these general value functions into our approximation architecture. Each general value function will predict an observation component. So this is the same as the agent asking, like, will the eye sensor turn on next time? And how far can I predict that into the future? Okay. So as I mentioned, the general value functions are linear functions of the observations. We are going to take the top k weights of each general value functions and take their corresponding observation components. So these are what we call a neighborhood. So they're not a neighborhood in Euclidean space, they're just a subset of the observations that correspond to the highest auxiliary weights. And we can say that because the auxiliary weights are highest, then these components are the most important in predicting the cumulants, being the ith component of a specific general value function. And the important thing here is that finding these top k inputs implies no notion of spatial relationships. So this is a diagram showing our architecture that we call prediction adapted neighborhoods. So let's say that we have a binary observation vector of 5 elements, and we have 2 general value functions. Each general value function is going to be used to form a neighborhood shown in orange and purple. And we're going to take that neighborhood and pass it through a dense layer shown by the matrix A. Then we pass it through nonlinearity, and we get 2 nonlinear features that we then linearly combine to form an approximation of the main value function. So the M1 and M2 here are sparse matrices of zeros and ones that select the top k inputs for the orange and purple neighborhoods respectively. And the important thing is that because the general value functions are being learned online and their weights are being adapted dynamically, the M1 and M2 matrices are also changing dynamically, and so is the connectivity or the topology of the initial layer of the network. And as I mentioned, this implies no notion of space. So this diagram shows 10 random general value functions that we have sampled and their auxiliary weights. So we show the in purple the top 10 auxiliary weights, in green the top 50, in yellow the top 100, and so on. And in the X here shows the location of the cumulant in the 2D space, or in 2D space. So we show, and this shows that if we take the highest auxiliary weights and their corresponding observation components, these observation components that form the neighborhood, they converge radially around each of the cumulants. So it's as if the general value functions were learning that the closest components to the ones that they're interested in predicting are the most important. But we haven't imposed any notion of space as we learn these auxiliary predictions. We also show that that prediction adapted neighborhoods appear temporally stable in this domain. So after 1 million time steps, the neighborhoods tend to stabilize. And finally, I'm also showing learning curves. So the plot here, the x-axis are the time steps in millions. The y-axis is the approximation error. The green line just shows a simple linear architecture. The orange line is just random neighborhoods. In blue is our approach, which adapts the neighborhoods online. And in gray, we have a calibration method, which hard codes the closest observation components in each neighborhood. So we show that the distance-based inductive bias is useful in this setting. Adaptive neighborhoods outperform random neighborhoods in this domain, and that an adaptive architecture approaches the performance of a handcrafted architecture. And although this plot is for an LTU nonlinearity, the trend also holds for other activation types like ReLUs and majority filters. And we also show that the more auxiliary predictions we use, so the more neighborhoods, then the lower final prediction error of adaptive neighborhoods, shown here in blue. And this trend also holds across other filters. Finally, some future directions. We want to explore how to optimize the network's hidden weights online. This is what I'm currently working on. We also want to evaluate how prediction adaptive neighborhoods perform in the reinforcement learning control problem, where we want to optimize what actions the agent is taking at each time step, and also explore how we can train this architecture and leverage it to multiple layers online. Thank you very much.